Okay, welcome to the Friday seminar series. And today we are very glad to have Dr. Yang Zhou from Texas A&M to give us a talk on his research on the traffic flow and then particularly the control of the traffic with a mixed vehicles of automated and connected vehicles and human-driven vehicles. Dr. Zhou right now is an assistant professor in the Department of Civil and Environmental Engineering at Texas A&M University. And he got his master's degree from the University of Illinois at Irvine-Champaign and his PhD degree from the University of Wisconsin at Madison. And before that, before he joined Texas A&M, he was a research associate supported by both the Department of Civil and Environmental Engineering and also the Department of Industry and Systems. Dr. Zhou mainly specializes in CAV, connected and automated vehicle control and the traffic flow analysis and the application of the AI in transporting and also the high fidelity simulations. He has published more than 40 papers in high quality transporting journals, including the Transporting Research Part B, Part C, and the IEEE transactions of the ITS, Intelligent Transporting Systems, and he also serves as a member of several committees, including the TRB Committee on Traffic Flow Theory, and also the ASCE Committee of Safety, and also the TDI, Transportation and Development Institute AI Committee, and he also serves the member of the editorial board of the Journal of Transporting Research Part C. So with that, please join me in welcoming Dr. Zhou.
Thanks. Yeah. Howdy, everyone. I'm so glad to be here. It's my great honor. So today my topic is the mixed platoon control strategy of connected and automated vehicles based on physics-informed deep reinforcement learning. Oops. Oh, here. And here is the outline of today's presentation. Firstly, I will go through the introduction a little bit and then move on to research objectives and overview restructure, and then move on to the methodology and provide some experimental results. Last but not least, I will have some summaries and point out the future works. Oops. And for the, as we know, with the advanced communication, sensing and automation functions of the vehicles, now we have the autonomous vehicles in the market, such as the Waymo and S-Arrow. So specifically with the accurate communication technologies that we can have the connected and automated vehicles to enable the cooperations among the vehicles. Together with some roadside units, we can further enhance the intelligence of transportation systems, and we can further have the automated driving systems, such as the connected automated vehicle highway systems, and so on and so forth. So as one of the traffic problems that we daily experience is the traffic oscillations. Specifically, we will experience this like stop and go traffics. And when we experience a little bit like stop and go at the very leading vehicles, then this stop and go phenomenon can further get amplified, which leads to traffic flow instability, traffic unsafety, emergency inefficiencies, as well as low travel efficiencies. So enabled by this like connected automated vehicles, we are aiming to develop a control based on this advanced control framework, such as adaptive cruise control, as well as the cooperative adaptive cruise control, to further dampen this traffic oscillation. So nowadays in the market, there are general three types of method. And first one is a linear or nonlinear analytical CAV controllers, and model predictive control, as well as traditional deep reinforcement learning controls, which all of these three has some pros and cons. Specifically, for the linear or nonlinear analytical CAV controllers, it is very implement and it's very convenient to conduct any types of stability analysis since they are analytical. Well, but it's really kind of hard to explicitly incorporate multiple objectives as well as the safety constraints. Well, for the model predictive control, whether you apply in the control theory domains, it can optimize multi-objectives in a flexible constraint framework, and it can achieve accurate control performance by a rolling implementation horizons. While sometimes it requires the formulated problem to be convex and to solve it online. Well, once the MPC is really difficult or very complex, it is usually computational demanding for the real-time implementation. Well, for the traditional deep reinforcement learning-based controllers, it can capture varied and stochastic characteristics by embedding this stochasticity in the training environment. And this neural networks helps to better solve this integrated non-convex control problems. And once you train it like a black box on offline, and it can be really fast computing in the online implementations. Well, sometimes when we do this like a traditional deep reinforcement learning practice, usually sometimes it is unstable for the training process, and it lacks interpretability due to this like black box property, and sometimes it's really poor for generalization, especially for some corner cases, it performs really bad. So in this sense, let me further refine this like CAV control strategies challenges for the mixed traffic, especially in terms of traffic oscillations. So firstly, how can we develop a fast, multi-objective, and stable control method to achieve like system level performance? And we know this like deep reinforcement learning approach usually is AI driven and data driven, and it's really hard to incorporate the control theories to facilitate the control performance. And another question is that how can we incorporate the traffic flow theory into this like a macroscopic CAV control? Furthermore, there are also some strong assumptions for example, the perfect communications between CAVs and perfect vehicle dynamics for CAVs. So especially in the context of mixed traffic, all of these like difficulties requires a new framework or new thinkings to organically integrate this control theory, system stability analysis, AI, traffic flow theory, simulation experiments together to have a better CAV platoon control or car following control. So with these challenges, we need to better understand, HDV stochastic, human-driven stochastic, and uncertain natures in the mixed traffic, as well as this heterogeneity of the mixed traffic of different topologies by different combinations. So given that, I will further describe our research scopes and overall structures. Specifically, we aim to develop by this research to a generic and fast computing deep reinforcement learning based CAV control suitable for any CAV-HDV topology. Essentially, this controller should be generic to any types of combinations. And then we propose a novel and generic car following structure to better capture the aggregated human-driven vehicle macroscopic traffic flow features to reduce the stochasticity and embed them in the microscopic CAV longitudinal control. And I will further explain this point. And we will further integrate the equilibrium concept as well as the consensus concept, widely known in control theory, into this deep reinforcement learning frameworks. And we also aim to achieve the multi-objectives containing traffic oscillation dampening, as well as car following efficiency, safety, and smooth acceleration. So this work, we aim to marry all this like a very advanced theory into an organic framework specifically for the control task. So essentially, we can divide the local stream communication environment for the mixed traffic into two broad traffic scenarios and fully connected automated environment, which has been analyzed very widely before. But we are focusing on the mixed local downstream environment of CAV, HDVs, and CAV topology. Because once you have any combinations, you can always find these topology structures. And here are some environment assumptions for our research to make it clarify beforehand. So we assume that the CAV state information, such as spacing, speed, can be broadcasted to the upstream CAVs through vehicle-to-vehicle communication in real time. And CAV can receive a real-time state information of its intermediate proceeding vehicles using the robust onboard sensors. And CAV can obtain its own real-time informations. And we also assume some vehicle communication mechanisms. And here we just use a signal inference plus noise ratios, as a representation. And the automation of CAV is assumed level 3+, and HDVs has no communication capability. So given the assumptions, let me further move on to our control frameworks. So given this CAV, HDVs, and CAV structures, we have state fusion strategies and deep reinforcement learning-based car following controllers. And then, once we output the car following control input, it will go through the vehicle dynamics. And the main philosophy of our control actually is based on this state fusion strategies, and it can better help to incorporate this macroscopic features to reduce HDV stochasticity. Let me further explain it. So we know that the HDV itself is very stochastic and uncertain, right? So any HDV's car following behavior could have some parametric stochasticities, and it can follow any kind of distributions. But if we aggregate them, for example, there are CVI and CVI minus M. So among them, there's MHDVs. So in this sense, if we treat all these MHDVs as an aggregated, you can treat it as a very big car following behaviors. Then we can aggregate these behaviors, right? So inspired by, for example, the central limit theorems. If you have lots of random variables of different distributions, once you sum them up and take expectations, you somehow can apply the central limit theorems to model its stochasticity. So that's why once there's lots of HDVs inside, we can model it as aggregated HDVs. In this sense, rather than capture the individual HDVs behaviors, we aim to capture this aggregated human-driven vehicles behaviors. In this sense, we can, to certain levels, we can reduce the stochasticity inspired by the central limit theorems. So in this sense, regardless of the number of HDVs among two CAVs, we can always find a novel car following pair structures. CAV follow an aggregated HDVs and follow a CAV. So in this sense, we can directly fuse the strategies. And here we use a constant time gap policies, which is actually equivalent to what the Newell's simplified car following models. And we define the local equilibrium spacings between each vehicle following this constant time gap policies, which equals to the current speed times the constant time gap policies plus the standstill spacings. And from control perspective, we define the equilibrium speed as the proceeding vehicle speed at each time. And for the multi-agent equilibriums. So we not just focusing on the CAV and HDVs that are adjacent. We can also compute the CAVs in equilibrium much far away from the downstream. For example, we can measure the deviation from, we can define the equilibrium spacings for vehicle I to vehicle I minus m as the similar to the constant gap time gap policy. It equals to the current speed times desired time gap between vehicle I and vehicle I minus m plus the aggregated standstill spacing similarly. So by that, we know, for one HDVs, it is just a very random car-following behaviors. Similar may follow the Newell's or not. But if we try to understand this like aggregated HDVs, then we have multiple aggregated Newell's car-following behaviors. Essentially, it is fundamental diagrams based on what we learned from the traffic flow textbook. So essentially, when we compute this like a multi-agent equilibriums for CAV I minus M's, and which equals to the summations of the gaps between vehicle I and vehicle I minus M for all like HDVs inside. And then we have this like a time variance distributions of this aggregated HDVs time gaps. And we know it is like a fundamental diagrams, and so that's why we better capture the macroscopic traffic features. So essentially, we use a simplified Newell's car-following models to bridge it, and from the simplified car-following models that we know, once you aggregate it, compute it, it's very related to the congested spacing as well as the kinematic waves. So using this, we define a real time estimate for this traffic waves, and then better guess this like aggregated time gaps for the aggregated HDVs within each CAVs. So by that, we can compute the deviation from equilibrium spacing between any vehicle I and any vehicle I minus M's. So, and it helps to reduce the dimension because we don't guess what's happening inside this aggregated HDV. We just focus on the HDV itself. And we apply, and we just feed forward to, firstly, the spacing between CAVI and the AHDV, as well as the spacing between AHDV and the CAVI minus M. And by some weighted average, then we can compute the general deviation from equilibrium spacing for this like a distance, as well as the speed difference. So based on that, we just try to incorporate this like a field state into this deep reinforcement learning characteristics, which has 4 components. The first one is the state, and then reward, environment, as well as the action. Specifically, we define this like state representation as the aggregated or the weighted average spacings and speed difference. And then we define the action as the vehicle's accelerations. And essentially, training a DRL is to find the optimal policies or the optimal parameters of this car-following neural network parameters. And then we need to better design a reward to realize this deep reinforcement learning training. So let's take all these elements are very important, specifically for the reward designs. Firstly, we have objective 1, which is the car-following control efficiencies, and we intentionally set as a quadratic summations of the state deviations. So this quadratic forms of the state actually is intentionally designed because we want to make it very similar to a linear quadratic regulator in terms of linear controls to keep the state close to the predefined equilibriums. And we further, and these terms can better help you to regulate all the deviations comes to the equilibrium. And we know when the equilibrium equals to 0, then we say the traffic reaches is equilibrium and it will become stable. So which can better help to reduce the driving safety risks. And secondly, we also minimize the eco-driving performance in terms of accelerations to ensure the driving comfort and eco-drivings. So with this, like a very similar structures of reward designs and together with the linear quadratic regulators, we aim to better achieve the stability. And the running cost for the DRL actually is summation of those two terms, and this is very practical routines for the DRL practice, and we let the refer function is the exponential terms weighted by the times, and then we just try to find the optimal policies. So, and here we just applied a widely known the distributed proximal policy optimization algorithms to train this like neural networks. And here are some hyperparameters. So given this like a very routine strategies, though very novel in terms of the state fusions, let's see how it works. And we further define some metrics such as cumulative damping ratios to measure the string stabilities, widely known in the control theories, and we also measure the local efficiency to see whether it is local stable, as well as we use the driving comfort terms by the square terms of the acceleration to see whether it can provide a very smooth control. And here is some examples that we run. And the first one is the distributed CAV controls by our method. Another one is decentralized CAV controls, which does not care what's happened for the downstreams, but only the vehicles that you are following. And we also compare with other strategies, for example, the linear-based CACCs and the model predictive control-based CACCs. So as you can find that our method provides the lowest damping ratios, which means that we can better stabilize the mixed traffic. And then we also provide the lowest driving comfort cost, which says that our control is better. And then we can provide larger average velocities based on this analysis. And we also conduct a sensitivity analysis for the mixed platoon with different penetration rate. And here, the green one is the positions, while the blue one is, they are all positions, but one is colored with the velocity, one is colored with accelerations. And we can find that especially when there's no CAVs, then once there's a little bit traffic oscillations, it will get amplified through the vehicular strings. And manifested by the speed will decrease and the acceleration will, oscillate. So, and we find that once the CAV percentage is around 40s, we can achieve a very smooth traffic controls. And we also conduct some generalization capability test by 150 data sets, essentially different traffic scenarios of different traffic oscillation characteristics. And we find that our control is really robust and that it can achieve the damping ratio regardless of the market penetration rate. But once the penetration rate increase, then it can benefit the traffic flow generally in terms of damping ratio, comfort, driving comfort, as well as average velocity. And we also set some irregular initial conditions to mimic the merging behaviors, and we found that our method can also quickly recover to the equilibriums, while we can still dampen the traffic oscillations. Then let me further move on to some summaries and future extensions, not limited to this work. So for this work, we just develop a generic and fast computing deep reinforcement learning based CAV control for any topologies, even under the communication loss, nested in the training environment. And we also propose a novel and generic coupling structures, CAV, aggregated HDVs and CAV, to better capture these HDVs macro traffic flow features. And we certainly integrate the control theory, traffic flow theories, and AI together, which achieves better control performance than the state of our methods. Well, then we are also thinking, essentially the road is not straight, right? Because in the urban environment, for example, the rural environment, then the CAV could be, movement is two-dimensional essentially, right? So that's why then the question comes to how can we readily extend this our framework to 2D dimension? So essentially, we apply a curvilinear coordinate, which the philosophy is very simple. And the one axle actually is along the center line of the path. And another axle is the anyone that's perpendicular to the tangent of this path. So it's really different from traditional Cartesian coordinate. But this one helps you to transform the traditional two coupling problems to actually one-dimensional coupling problems. So think about this path is like a cotton, right? Once you stretch it straight, then the length does not change, but the only features is the curves of the length, right? So by this curvilinear coordinate, we further apply our method to the couplings and link keeping driving tasks. And here are some results. And the first part is geometries, and you can find this is a leader, this is a follower 2, follower 4, and we can see that once you apply the same philosophies, you can achieve very minimal lateral deviations for each vehicles. Even under very special scenarios, as you can find, the road is pretty curved, then it can still achieve some very good link keeping results. While for the position-wise, even under different desired speed, then you can still achieve very stable result, and it is string stable, which means that you don't have any traffic oscillations, even overshooting. So furthermore, bearing this like 2D extensions, we also focus on, for example, let's forget about the car following efficiencies, right? Because the safety is usually the first concerns, especially for the automobile manufacturers. So then we further extend the scenarios to see, hey, how could you conduct any type of active safety analysis for this like 2D dimension or very complex dimension? So, and we found that, currently the majority of the active safety tools, especially for this 2D scenarios or even more complex scenarios, everything is so related to the TTC, which is time to clear metrics, and design philosophy is simple because they basically assume the vehicles remains constant speed for the TTC, right? And usually it can only be applied to one-dimensional or piecewise one-dimensional traffic scenarios. But it cannot really help you to better understand the safeties, especially for these 2D coupling scenarios or even merging as arrow. And here is some roadmaps of by another studies, but as you can find, everything is related to TTC in terms of active safeties. And specifically, we found that usually this type of safety analysis is also without considering the vehicle dynamics. Though our reinforcement learning has lots of vehicle dynamics, communication topologies, etc., right? And we also have our self-design control laws as well as human-driven vehicle behaviors. But in this type of mixed traffic analysis, regardless of the traffic scenarios, then they don't consider those, as well as the application limitations for the active safety analysis. So that's why recently my lab actually aims to systematically extend those like current active safety analysis with both theoretical approximations and help with digital twin and advanced AI techniques to help you to be generic to any kinds of highways, capture high-order vehicle dynamics, and actively predict the ambient traffic environment. But this is what's ongoing by my lab, and actually this is just get funded by the Federal Highway EAR project, Advanced Exploratory Advanced Research Project, and I would like to further disseminate this result once we made some substantial progress. So, and if you're really interested on this like control strategies, then you can also find those type of research that we already published, and I would like to answer all types of questions, and you can also email me. Thank you so much.
Okay, thank you, Dr. for your presentation. And now the floor is open to questions and comments.
Yeah, go ahead, please.
Sorry. I've seen agencies in the area, they've used kind of that advanced visualization for safety. Like they'll use kind of predictive tools to, identify hotspots that, can be targeted for safety countermeasures. I guess, what are your thoughts on like applying, more advanced visualization tools for like local agencies to apply some of these tools and, reinforce that advanced, like, deep learning tools just for their safety tools, but also for planning?
Yeah, sure. Thanks so much for the question. So firstly, for the visualization, I believe they need to use some simulation tool, because you can find here what I have right now is they are all numerical, right? But this is not enough for sure for lots of different stakeholders. So that's why we need a better tool. But for this type of work, it's numerical, but usually they require it to for example, the sumo or color co-simulate together, then they can better visualize what's the potential safety risk, etc. But what I mentioned here is that, oops, oh yeah, this way is the correct way. But in general, they cannot understand this like potential risk in a correct way by this very oversimplifications, as well as they cannot apply to any types of geometrics, right? So in this sense, so that's why this work is done, but you can nest it inside this like color sumo co-simulations. And actually Federal Highway, they are also sponsoring this type of research for this sumo color co-simulation, and they call it as Karma X. But essentially, this should be something missing for this type of analysis. Yeah, thanks.
And yeah, just to follow up with that, because of the risk of oversimplification, do you think that kind of limits the scale that this research can be done? Like, does it have to kind of remain on smaller areas or smaller study areas versus doing like a larger metropolitan study?
Actually, it's related to fidelity issues. So for example, let's say this type of work there. So for example, the TTC, right, time to clear, they fairly assume the vehicle remains a constant speed, even for the piecewise 1D, right? So they assume that steering wheel, let's say steering velocities, etc., will not change. These assumptions reduce the fidelity of the risk analysis. So that's what I mean. And even for like a mega cities, right? You have like lots of geometries, like roads. If you want to do very microscopic analysis, because the macroscopic traffic safety analysis is kind of aggregations of the microscopic one, right? What I mentioned is that even for the very microscopic features, they cannot do that really well because they cannot better handle the geometries. But if you, as I said, oops, I usually, let's say for this type of scenarios, because what we do is we use a different coordinate, right, to make it straight and plus some curves. In this sense, we can still make the traditional TTC or something still can still hold for these scenarios while changing the coordinates, and with some like more modern like characteristics, then we can better enhance the fidelity. That's a main issue. Yeah. Thank you.
Thank you.
All right, any other question?
Yeah.
Yeah, one.
Thank you for the intriguing presentation. Yeah, actually, before ask questions for you, I want to follow up his questions. Yeah, I'm wondering what kind of visualization tools are you expecting from a stakeholder perspective? Let's say I have a plot of time to collision similar to the traffic diagram. Well, the red spot could be something you want that highlight the danger in a specific zone. Would that be something you're expecting? Yeah.
Visualization or model that they can do to ensure that those funds are going to the right places to meet those.
Yeah, I see. Actually, I saw an interesting slide. There is a sign on highway says congestion ahead for next 20 years. So actually, that we can put danger zone ahead, saying this is a high risk zone because we can monitor, we can see the time to collision in this specific zone is usually higher, the risk is higher. So I think that's close to what local agencies might want to see. Yeah, and your second question is related to how can we scale up this kind of microscopic research. I recently heard some news from self-driving industry. They managed to scale up the lateral control. So this is like a longitudinal control. For lateral control, say you have some car agnostic planner design to improve the performance of a car. But when it comes down to every car, your car, my car, different ages, different conditions, how can we guarantee the same policy can work on both of our cars? That's the issue, challenge in scaling up our research. So there are some control work going on to address this kind of problems. And I just want to know this is possible. We already seen some hopes, some success in the lateral control research direction. And we are ongoing research is here to try to solve the problem for the longitudinal direction. Yeah, maybe it would take 1 or 2 years, but it's very possible. Yeah, thank you. Yeah, thank you.
Yeah, but yeah, let me can I supplement a little
Sure.
bit based on your comments? So firstly, we do have the lateral control here because as you can find, we still keep the lateral deviations, and just by expanding the states. So yeah, so that's a great question in terms of like the funding allocations for like a very so identify the potential high crash, high risk crash rate sites, right? So in this sense, once you have this type of analysis, you can simulate like 1,000,000 times, right? Via like a parallel computing, and then you can, based on that, you can identify what's the potential risk side, and you can then allocate the funding to it. So, and if you like, I would like, after class, I can send you several papers that are written by my students, and they get like a HSIS first award by Federal Highways. It's very safety related, and we also develop we call it equitable traffic crash prediction systems. And yeah, I could let you know. Yeah. Yeah, thank you.
Yeah, some questions for you.
Yeah, cool.
Yeah. First, I'm wondering, can you share some insights into the stochasticity in human drivers?
Yeah.
I noticed you had 2 papers. My question is actually, do you find the stochastics only in acceleration or both acceleration and deceleration? And do they actually have independent random process
Okay, cool. Yeah, that's a great question. So let me attempt to, we find that firstly, we know for individual drivers, right? For individual drivers, it is very stochastic. And for example, by this paper, I kind of like cannot distinguish what's the correct, for this one.
Yeah.
These two. Firstly, there are several things, for even one drivers, right? Individual drivers, we find there's intra-heterogeneities as well as inter-heterogeneities for human drivers, right? And even based on our approach, especially this 2-1, we also find even the law, or let's say the functions of how the response is really different. So in this sense, if you try to, so that's why in our papers, rather than capture individual vehicles' behavior, we capture a string of the vehicles' behavior. Because we know macroscopically fundamental diagrams works, right? So especially, I believe you are also like a expert in traffic flow theory. The aggregation of the behaviors of human drivers, follows the triangular fundamental diagram, though there's some stochasticity inside. But, but once you sum it up, right? Sum it up, do some expectations. Naturally, by central limit theorems, we know you should follow normal distributions. In this sense, we kind of reduce the stochasticities. But I agree with you, for individual drivers, even a very small random noise may result very different behaviors, vary from person to person, and also varies over time. So in this sense, so that's why we do this like aggregated HDV behaviors in our control framework.
Yeah, I agree. Actually, the errors for human drivings, they're compared to the mean, and the mean is the Newell's model. And I want you to comment on if the deceleration process is more deterministic compared to the acceleration process. I'm not sure if you have looked into this problem since you have shown data and the stochasticity topic here.
Yeah, so that's a good problem. So actually in this framework, no, because
it looks like you're treating them similarly.
Yeah, we didn't really distinguish the acceleration or deceleration process because we used the Newell's model to capture it, right? And the Newell's model is symmetric. So, but one thing that we accommodate this behavior is that we real-timely estimate this Newell to somehow reduce a little bit, like something varies, from the simplified Newell's CAV-following models, because we estimate in a real time, try to, reduce this type of impacts. But I agree with you, because Newell is symmetric. So if we use asymmetric and simplified Newell's CAV-following models, and then it could work better. But still, by these philosophies, it still performs pretty well, than the state of our method.
Okay.
Yes, thanks so much.
Yeah. Next question. Actually, I don't quite get it about the DRL framework here. So, can you briefly elaborate on what is the state for the CAV here? And I kind of get the point that you try to get some aggregated features, try to treat all the vehicles between CAVs as a whole based on Newell models. Then those aggregated features are sent to the following CAV. Then the following CAV, starting from there, what is the following CAV doing?
Yeah, sure. Firstly, the state actually is a weighted average of two CAV-following process. One is control CAVI follows AHDVs, and the AHDVs follows the CAVI minus M. We consider both spacings, and by weighted average those spacings, then we can compute, what's the deviations from the desired equilibrium spacing for those two CAV-following process, and we fuse it together by weighted average. So that's what we call state fusion strategies, because we consider two CAV-following process. CAVI follows AHDV, and AHDV follows CAVI minus M. And by this, by that, because if the AHDVs will deviate from its equilibrium, it will keep like generating these oscillations, right? So that's why by this weighted average, we kind of bestow our controller with some predictive capabilities, because we also want to anticipate what's happened for this AHDV follows the CAV-I minus M. So that's how we do this state fusion strategies. Basically, two-coupling process in a holistic manner.
If I was driving that CAV, what I would do is to observe the several cars in front of me. Maybe I will try to see the oscillations in the HDV platoon. And the strategy for me to dampen the oscillation would be keep the distance and, let's say, respond, do not respond harshly to the oscillations in front of me. I'm trying to find the intuition behind your DRL policy.
Yes. Yeah, it's very similar because you react to multiple HDVs in advance rather than one HDVs in advance. So yeah, it's very similar, but it's not like driving very slow because you also want to maintain your desired spacing by yourselves to, because some CAVs could be also very selfish, right? So you have your own desired spacing. You just better anticipate, but it's not, anticipate, but not just wait or,
Yeah, then the question quickly comes up, why do we need connectivity here?
Because, if you don't, because, for example, you don't know this vehicle spacing, you cannot directly, where's the pointer here? Yeah, you cannot measure the CAV standard adjustment for you. You can only measure via, for example, here, vehicle I minus M, I minus 1, as well as HDV I minus M minus 1. Or I minus M plus 1. You can only measure those two vehicles, but you cannot measure something in the middle because the radar or the LiDAR cannot, go measure those something in the middle. But CAV I minus M can measure CAV I minus M plus 1, while CAV I can measure CAV I minus 1. So that's a trick that we're playing with.
Yeah, let me change the question another way. So let's say the CAV follower here, it is a string stable ACC, just reacts to the immediate leader. And my question is, what does connectivity bring more here to the table? What kind of information can help the CAV make more informed decision than a simple string stable follower to the immediate leader?
Yeah, sure. Thanks. So essentially for string stable ACC, let's say, it only reacts to, the behaviors of vehicle I minus 1, right?
Yeah, it's leader, right?
Yeah, it's proceeding, very adjacent proceeding leaders. But by this vehicle communications, you can know what's happened pretty downstream, right?
Yeah.
And then you can anticipate its behaviors at large. So that's why, that's why our control method essentially is better than the decentralized control, because the decentralized control only reacts to the very adjacent followers.
Yes. The good news is that ACC can also do anticipation now. It's kind of not the practice, but can be the future. Since we have cameras, let's say like Tesla, it can detect multiple vehicles in front. So I can envision maybe in the future, one single vehicle can do all of this without requiring connectivity. Yeah, but just my conjecture.
Yeah, that's cool. Yeah, I do agree. But once you can marry, then you can still apply these methodologies very similarly.
Yeah, for me, the anticipation, the benefit is more related to the safety level, since you can maintain a small spacing, but you can also predict the safety incidents that might come up in the future. So if you have good anticipation, you can strike a better balance between string stability and safety.
Yeah, I agree with you. Yeah, totally. Yeah. So essentially, once you can better anticipate, it's not really just related to safety as well as energy efficiencies in general. Yeah, sure.
Okay. Thank you for answering. Thank you.
Thanks.
Okay, any other questions or comments? I don't see any inputs from the online attendees.
You really hear me?
I got a couple of like questions.
Yeah, cool.
I'm not in this field, but seems to me that your model framework is mainly for the longitudinal control of the vehicle movement. So that can this accommodate the interruptions from like lane change on and off ramp intersections?
Yes, actually, that's what I'm writing right now. I'm writing a proposal called the universal control laws for this one. But in general, think about it, right? That's a good, really great point. Oops, I just messed up with a direction. Let's say this is a 2D car following, right? And think about there's one vehicles will merging. If you, let's say, firstly, this is changed from 2D to 1D already by this curvilinear coordinate because the path is already one axle and it's on lateral behaviors. If there's merging, for example, the vehicle CAV I-1 is some vehicle that's gonna merge in, but on another curvilinear coordinate. But you can still put this like two curves as one curves, by we call like a virtual platoonings. Because once it merges, then it's still coupling behaviors after the merging, right? So by this like anticipation, we also did some problems very similarly by this virtual coupling concept, or even we call time varying virtual coupling concept. But still, if it's merging problem, then this is a ready extension. Well, for the intersections, it could be very tricky. So that's why we write a proposal about it. But essentially, my intuition and answer is yes, it can also be changed to a certain level of coupling problems by very like a comprehensive systematic, like a dimension reductions and like a virtual coupling concept. But this philosophy still holds, though not happened yet. But my intuition is, you can apply coupling to every driving tasks, especially microscopic driving tasks, by this like a very intuitive 2D extension. Yeah, thanks.
Thank you. I got another question is, in your model, I think you assumed the level of autonomy of the vehicle, CAV is level 3 or up. And I assume that the HDV is the level 0 with no autonomy
Yes.
in the vehicle. So my question is, how about like different levels of autonomy, so like a level 1 in the so-called HDV human-driven vehicle? So will that impact your model results?
Yeah, so here, thanks so much for the question. So here, what we assume is that we can control the vehicle by ourselves regardless of, because once it's a level 1, essentially is a cruise control, then level 2 adaptive cruise control with some link keeping functions. So that's why we assume, at least they have these functions and then we can control it. So that's why it's a prerequisite. Well, for like a level 4, level 5, it means that for every scenarios, then there's no need for the human interventions happening. So, but it's very related, but essentially, because once it's level 1, they are not that intelligent. So essentially, they don't have these LiDARs. They don't, gives you the right to connect to the CAN bus of the vehicles, and you cannot control it. So that's why we made this assumption. Thank you.
Thank you. I got another question. Like, I think your model is mainly for the microscopic control, like vehicle trajectories at a localized region, like on some low segments. Last week we have Dr. Jorge Lova from Georgia Tech and who give a talk here in the same room. I think his perspective is more from a network level. He talked about like a fractal and the chaos, the instability of the system due to the small perturbation of the inputs or so the original states. And so my question is like, have you considered like expand this to a system level?
Yeah, that's a great question. So there actually I've been doing something related to the macroscopic features, but it's not directly to a very macroscopic level. What we did recently is that we derive analytical solutions for the fundamental diagrams for the mixed traffic. Fundamental diagrams means density and flow relationship over a segment. And we found that we call like a stochastic and dynamic fundamental diagram, which is also supported by the National Science Foundations, but that's only for segment. And we further try to expand it to a intersection level, because if we can change everything to car-following problems, then the capacity analysis, system level stabilities, then this can be readily given, because car-following models is widely known. But only to this scale. We didn't really think about the network level scales stability issues. Yeah, thank you.
Okay. Any other question or inputs from the audience? And I don't see any inputs from the online attendees. So if not, we're gonna end the seminar. Thank you, Doctor, for your
thanks so much
and the discussion.
thank you.